Welcome back everyone. Today's video is an explanation of problem F from the AtCoder Beginner Contest 309. I have provided the correct Python code in the video description, so please check it out after listening to my explanation. Let's begin with the problem statement. We have n tuples denoted by Si, and each has three values. A tuple represents a box, and its values represent height, width, and depth respectively. Every box can rotate, so each tuple can swap the values as desired. Our problem is to check every pair of boxes Si and Sj and all possible rotations to determine whether there exists a pair such that one completely includes the other. Let's see it with the right example. By rotating S2 and swapping its height and depth, we can make its height, width, and depth smaller than S3's. This means that S2 can be included in S3. Since we've found a pair that satisfies the condition, the answer for the example is yes. Let's proceed to solve the problem. First, we'd like to obtain a mathematical expression for the condition that one box is included in another. Since a rotation of a box is equivalent to a permutation of its height, width, and depth, the condition is equivalent to saying that there exists a pair of boxes Si and Sj and a permutation of each box such that each variable in Si is less than the corresponding variable in Sj. However, dealing with permutations makes it difficult to handle this condition. Then, we notice that there's no need to consider all the permutations for each box. It suffices to consider tuples with variables arranged in ascending order. To prove this, it's sufficient to show that if there exists a pair that satisfies the condition for inclusion, then we can construct a pair that satisfies it and has variables in ascending order. I'll explain it with the example below. First, we permutate S1 to arrange it in ascending order, and then permutate S2 using the same permutation as S1. Although S2 may not be in ascending order after this permutation, we can swap its first element with the smallest element in S2. This swap maintains the relative order between the elements of S1 and S2. Similarly, we can swap the second element and the last element of S2. As a result, both sequences become in ascending order as desired. Now, we come to the main problem of 309F. We assume that the variables of each tuple in the array S are in ascending order, and our problem is to determine whether there exists a pair Si and Sj such that each variable in Si is less than the corresponding variable in Sj. We will focus on this problem from now on. At first, we may think about checking all the pairs Si and Sj, but it's impossible because the size of S is n, which is at most 10 to the 5th. So the number of pairs is n chose 2, which takes 10 to the 10th. That's why we need a better algorithm. I'll show you this with the examples on the left of S. But here, I have a slight warning about the examples. The variables of the tuples in them are not in ascending order. This is because the condition is too restrictive for implementing the algorithm. I chose these examples to demonstrate the broad range of applications for this algorithm. The algorithm begins with sorting the array S in ascending order of the first variable x. This allows us to disregard the information about x. I'll explain later how it works. You don't need to concern yourself with the order of y or z. So, as you see in the example, there's no problem if tuples with x equals 4 are not in complete ascending order. Next, we prepare an array z to store the y-coordinate and z, so we define its index as the y-coordinate and its value zy as the minimal z-coordinate for the given y. We initialize its value as infinity. The preprocessing of the algorithm is now complete. From the next slide, we iterate over s and update z of y. We come across the first element of s, that is 1 to 7, and we'd like to add the point on the yz plane. To achieve this, we simply update z of 2 to 7. The initial operation is now finished. We have the second element of S2, 2, 3, 5, and as before, we'd like to add the point on the YZ plane. But before doing that, we need to check if there is a point less than S2. We want to know if there exists a pair Si and Sj satisfying each coordinate of Si is less than the corresponding coordinate of Sj. See the yellow rectangle in the diagram. If there is a point in the rectangle, its y-coordinate and z-coordinate are less than the corresponding coordinates of S2, respectively. Interestingly, its x-coordinate is also less than the x-coordinate of S2. Since we sorted S in ascending order of x, the coordinates of points added before S2 always are less than the x-coordinate of S2. Hence, now, we want to know if there exists a point in the yellow rectangle. This is where the array z becomes useful. We calculate the minimum value within the range 1 to 3 of array z. If the value is less than the z-coordinate of S2, it directly indicates that there is a point in the area. In this case, the value is 7, which is not less than 5. Therefore, the pair S1 and S2 is not the required one. To add S2 to the diagram, we update z of 3 to 5. We have the third element of S3, that is 3, 7, 5, and we perform the same operation as before. First, we calculate the range minimum of array z, and then update the value of z. Note that we don't include the boundary of the area. We must move on to the next point. Here is a slightly more complex case in the algorithm. What if there are points with the same x-coordinate? We mustn't calculate the range minimum and update the value for each point individually. The reason is shown in the diagram. If you do that in the order of the blue arrow in the diagram, you may regard the pair of these 2 points as a required one. However, since their x-coordinates are the same, they are not in an inclusion relationship. How do we avoid this error? One approach is to check all the areas induced by the points with the same x-coordinate before updating array z. In this way, when taking a range minimum, The x-coordinates of all the points in the diagram are always less than the x-coordinate of the new point. After finishing the checking part, we simply update the value of Ri z at the same time. This avoids the problem. Therefore, in practice, we not only sort S in the preprocessing stage, but also divide S into several groups based on the x-coordinate. We come to the element 536. The last warning is that when updating Ri z, we don't always change its value. The update formula is defined as shown in the slide. The last element is 664, and this is a successful case for the algorithm. When the range minimum is less than the z-coordinate of this element, we must return yes and immediately terminate the algorithm. However, if we can't find such a pair and come to the last element of S, we must return no. This completes the explanation of the algorithm. Before we conclude this video, I'd like to mention some warnings and the time complexity of the algorithm. First, Ri z should not be implemented as a simple list. As you can see, it requires taking range minimums and operating its values. To achieve this, we should use a segment tree as the data structure for Z. It allows us to perform these operations in logarithmic time. Additionally, the indexes of Z should not be too large. Although we can handle up to 10 to the fifth elements, the possible values range from 1 to 10 to the ninth based on the problem constraints. Since the indexes of Z represent y coordinates, we must resize the y coordinates in S and adjust them to fit within the range of 0 to n. We can do this because the number of unique y-coordinates in S is at most the size of S, which is n. Therefore, we need to include this operation in the preprocessing stage of the algorithm. Finally, the total time complexity is as follows, and it is acceptable. So we have successfully solved this problem, and I have completed the explanation. If you have any questions regarding the problem or any requests to solve other ABC problems, please feel free to comment. Thank you for watching the video.